Ever heard of Ramanujan?
Yeah. No.
It's a man. He lived over 100 years ago. He was Indian. Dots, not
Feathers, yeah.
And he lived in this tiny hut somewhere in India. He had no formal education. He had no access to any scientific work.
You, sir?
But he came across this old math book. And from this simple text, he was able to extrapolate theories that had baffled mathematicians for years.
Yeah, continued fractions. Yeah, he wrote it with a...
Well, he mailed it to Hardy.
Yeah,
Hardy in Cambridge.
yeah.
And Hardy immediately recognized the brilliance of his work and brought him over to England. And then they worked together for years, creating some of the most exciting math theory ever done. This Ramanujan, his genius was unparalleled, Sean.
I've been going over your work on partitions. Seems to me you're on the verge of a major breakthrough. So now you've begun to embrace some proper rigor. I think you should meet Major McMahon. He's the leader in combinatorics at the university and also happens to be one of your most vocal opponents. He says partitions can't be done, especially by the likes of you.
Then you better start counting very high.
Enter at your own risk. Bloody nerve of you both. You fail on primes, and you think you can just turn round and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
No, I will. By hand. By slow and painful addition, and then you can be absolutely certain that whatever formula you two can dream up will be quite wrong. Then you can crawl back under whatever rock you came from in India, and we can put to bed this charade of yours, Hardy. Now, how high do I have to go?
P of 200 should do. I really can do it.
What are partitions? A partition of a number n is a way of writing n as a sum of positive integers. So take the number 4. You can write 4 as a sum of positive integers in 5 different ways, so the number of partitions, or ways of breaking it up into parts, is 5. The partition counting function evaluates this for a given integer n. So how many ways can you write 12 as a sum of positive integers? That is, what is P of 12? To organize this, we must group the numbers of parts and explore the possible combinations. For one part, it's just 12. For 2 parts, you can have things like 11 plus 1, 10 plus 2, 9 plus 3, and so on. How many parts are there in 3s? You could have 10 plus 1 plus 1, or all the way down to 4 plus 4 plus 4. Continuing in this fashion, the number of parts begins to grow rather large. And although there is a finite number of parts, predicting how many there will be seems to be a little cumbersome. If we evaluate all the cases for P of 12, the final total is 77. There are 77 different partitions for the number 12. So as you can see, even for relatively small numbers, the number of partitions is large. Why are partitions so important to number theorists? Well, they answer the question, in how many fundamentally different ways can something be broken apart? Organizing structure. Partitions let you classify numbers, understand how numbers are built, and detect patterns that are not obvious. On another level, they reveal hidden multiplicative structure. From partitions you get generating functions, Euler products, and divisor functions. From a physics interpretation, partitions describe how energy can be distributed among states. Each partition equals a statistical microstate. The total number of partitions equals the total number of configurations, and this is literally how entropy is computed. For the sake of symmetry, partitions classify symmetric group representations and ways symmetry can break things up. On a computer science and algorithmic level, partitions show up in optimization problems, resource allocations, and how we distributed limited resources. But for number theorists, partitions lead directly to modular forms, Q-series, congruences, and simply counting deeply analytic structures. So the real reasons that they matter are that partitions reveal how complexity emerges from simple rules. You start with just addition, and you get exponential growth, hidden symmetries, modular behavior, and deep formulas that emerge. The most unexpected way to count numbers: playing with partitions. Consider the Q power series, and observe that applying the differential operation Q times d by dq on both sides, we obtain a sum whose coefficient picks up a weight equivalent to its term exponent. Now, if you recall the Euler product from our previous video here, E of Q, and we take the logarithm of both sides, turning the left-hand side product into a sum, and then we apply the differential operation from before to this sum, we get a unique expression in terms of q to the n, one that is rational. And let's play with that expression just a little bit, noticing that it resembles a geometric series. Q to the n over 1 minus q to the n is an expression that as a power series can be expanded this way. And then multiplying this series by n, we get the following. This raises a natural question that how does one calculate a coefficient of such a series? So imagine we want to calculate the coefficient of the q to the mth term. How do we do such a thing? Well, let's produce a little data. So consider the term q to the sixth. We need all expressions of the form q to the n times k, or q to the m, which here is q to the sixth. So n and k are all the factors of 6, and if we list all the contributions, we can tally the results. Each term of the power of the form n times k yields a coefficient of n, and therefore the sum of those contributions here results in 12. Thus, each term of q to the m contributes all the values of n that divide m. And we can say that mathematically this way. M is equal to n times k, so n divides m. So we define our sum as a power series whose coefficients we will define as sigma of m, represents a function that sums the divisors of m. That is, our original geometric power series viewed as a double sum means that the sigma coefficients are generated as the sum of the divisors of m. And so we have this double sum, which we can then redefine in terms of this sigma function. The sum of n, all the divisors of m, is this function sigma, the sum of the divisors of m. And this is generating the coefficients of our power series. And thus, an identity is established. Taking this identity, we can then make a substitution into our log equation from before, and we find the following result. We find a way that we can connect partitions to divisors. Now we're presented with the challenge. How does one calculate p of 200? If you listed one partition per second and never stopped, it would take you roughly 126,000 years to do so. Therefore, an algorithm must be developed. Recall that the reciprocal of E of q produces a power series with coefficients generated by the partition counting function. Taking the log of both sides allows us to express the left-hand side of our function equation, and bringing back our identity, we see that we want to apply the differential operator to this new log equation. And so, we have the relation between the divisor series and the partition series. Next, let's call the partition series capital P of q, and it is the reciprocal of E of q. And so by substitution, we have this relationship. Applying the logarithmic differentiation on the right-hand side and then rearranging some terms, we get a clean equation to explore. And because of the nature of this differential operator, we get a beautiful relation. And this is the beginning of a recursive relationship. One of the reasons Ramanujan enjoyed logarithmic differentiation so much. So now from this relationship, we have a Cauchy product on the left-hand side. And matching the coefficients of the Cauchy product of the sums, our recursion will begin to close. Matching the coefficients, we get this relationship. Partitions are recursively defined depending on the action of the divisors. And we can establish the efficiency of this algorithm up to a value of capital N. In this scenario, the cost of an arithmetic sequence, which requires n squared computable time, is about how efficient we can rely on this recursive formula, this recursive algorithm. We represent that computability time as big O n squared. But is there a more efficient way to do this, a more faster way to do this? In fact, there is. Recall Euler's pentagonal number theorem from our last video. Could this provide a better recursion, exploiting the mod 5 symmetry, and reduce the complexity of our algorithm? We recognize the relationship that P of Q times E of Q is equal to 1. And we build an expression of these series and begin to match the coefficients, expanding the product term by term. As we do so, we will begin to build a pattern for the coefficients. So observe that if we also expand capital P of Q, the sum of the partition functions as a power series, we get this relationship. Multiplying that series by negative Q gives us this. Multiplying that series by negative Q squared gives us this. And multiplying that series by Q to the 5th gives us this, and so on. And so we can take these relationships and substitute that into the equation above. And thus, matching coefficients, we begin to develop the relationship. Here we have the following relationship. Since the right-hand side is equal to 1, P of 0 is equal to 1, and all the coefficients remaining are equal to 0. So now we can extract the pattern. The coefficients of Q to the n in full product is here. And what we notice is that the pentagonal numbers begin to reveal themselves in the recursion. And if the coefficient of every Q to the n for n greater than or equal to 1 is 0, we have this relationship which we can then solve for P of n. And so, depending on our particular n value, we have a finite number of terms necessary, according to the pentagonal number theorem, to calculate this algorithm and to use this to get the partitions. This is Euler's pentagonal recursion. The cost of this recursion is on the order of big O n raised to the 3/2 power, so asymptotically this is more efficient. Now, using Euler's pentagonal recursion, you only need a finite number of pentagonal offsets that are less than or equal to n. So if n is equal to 200, we need only 22 values or offsets to calculate P of 200. This represents a huge compression in our algorithm. So now we need to generate some data. Creating a table of values for P of n, and using the recursive relationship to build this table shouldn't take too long to arrive at our answer. And thus, here, slowly, one by one, we generate our terms. For n equals 3, we're using the offsets 1 and 2. For n equals 4, we're still using the offsets 1 and 2. But when we hit 5, we then use the offsets 1, 2, and 5. And until we reach 7, we're using the offsets 1, 2, and 5. Then we increase our value here to the offsets 1, 2, 5, and 7. So you get the idea of how this recursion builds, but only uses a finite number of offsets so that those offsets can reduce our calculational complexity. So to calculate P of 200, we would need to find all the previous values listed here from our pentagonal offsets. putting the work in, we get the final value of P of 200 to be 3,972,999,029,388 different ways to partition the number 200. But still, is there a better way to do this? And if so, how? The Hardy-Ramanujan asymptotic approximation formula. Srinivasa Ramanujan and G.H. Hardy worked together and derived a formula for approximating P of n for large values of n with rapid convergence, and this is the formula that they came up with. So, you see, Ramanujan didn't need exact values to find exact values. He would approximate until a number stabilized to a known value, or at least to an integer value if that is what he expected. And this is often how he worked, and even developed a few correction formulas. So at first approximation, he gets an overestimate for P of 200. Using a few corrections, he begins to stabilize his value. You see, the more corrections he makes, the integer value begins to settle down. And once he gets the decimal values to begin to be where they stabilize, he knows he has hit the integer value that he needs. And it only takes him a few correction terms to arrive at the stabilized value of P of 200. Ramanujan was a remarkable genius, and now he was being put to the test.
Well, here we are, P of 200, the moment of truth. You know, I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
From his mathematical upbringing, he thought like no other. And his thoughts, his insights, showed something deeper was happening. He saw hidden structure with clarity of mind. But what if his formula was telling us about much, much more? Consider the concept of entropy. Entropy measures the number of microscopic configurations consistent with a macroscopic system state. It's the number of ways you can arrange smaller parts of a system that result in the same overall larger state. S is equal to the log of the number of possible states, S being the entropy. So if we let P of n describe the number of possible states a number n can be in, the entropy of the system is then measured using the formula S of n is approximately log of P of n. So we can connect entropy to partitions. And using Ramanujan's approximation formula, we can plug this into the log formula and get a value of the entropy, S of n, to be approximately equal to this expression. The complexity of partitions doesn't grow linearly, it grows like the square root inside an exponential. Partitions are not just about numbers, but about measuring how rapidly structures can emerge. The same growth is observed in thermodynamic entropy, black hole physics, and quantum systems. But where does this mysterious formula come from? How did Ramanujan derive this mysterious formula? For that, we'll just have to wait till next time. But with that, thanks for watching. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.